was hooking up, I took my PS4 to somebody's house and I brought it back and hooked it back up to the internet. And I was like,
all right, so let's play around with the ODP and with some approaches to using GDB. So I'm going to stick in this directory where I am. I'm going to add a G switch to my compilation so that I get debugging information. So the goal here was to take a linked list, right, in the form of an array of struct nodes and return the data value of the first data node. Okay, and if the first data node didn't exist, then you return a 0 and you set this error variable to a 1 to indicate an error condition. I lost my, yeah. Hey, it's me. I gotta throw some tape over my camera. So get first. So we pass it a struct node array. And we also passed it a pointer to an integer. And this whole thing returned an integer. And so error was a flag that we were going to set to indicate whether an error occurred or not. Okay, and let me call this struct node star LL for linked list. So we have a linked list in an array and we have a pointer to an integer, which means we can change the value of that integer in the caller. And there's two possibilities. The first possibility is that all we have is a sentinel node, in which case we should return 0 and we should set error equal to 1. Or it could be that we have at least one data node, so the sentinel is pointing somewhere other than my null, and let's say we've got a 17 here. In this case, we want to return a 17 and we want error to be equal to 0. Those are the only two behaviors from get first. So if there's a first data node, return its value with error equal to 0. If there's not, if the list is empty, return a 0 but set error equal to 1. So what could this look like? Well, the sentinel always starts at index 0. And we've got data next invalid. With an empty list, data, we don't care what its value is. Next is going to be -1. Valid's always going to be 1. That's an empty list. Doesn't matter what's in any of the other locations. In this case, the sentinel is still valid. It's got some data value we don't care about, but its next field is something other than my null. So maybe it's a 2, saying that the node that follows, which is the first data node, is stored at index 2. So at index 2, we'd have a 17 that would be valid. And next could be, it could be my null if that's the end of the list, or it could be the index of some following node. Doesn't matter. So the idea is we're going to look at the sentinel, LL bracket 0 dot next. If it's -1, set the error to 1 and return 0. Otherwise, see what value is stored at LL bracket 0 dot next, and then look at LL bracket that value dot data. That's the value we're going to return. Right? Set the error to 0 and return that. So this would be something like LL bracket 0 dot next. So maybe that's I, and then we want to return LL bracket I dot data. So when you're working on these ODPs and you write me with a question and you say my code's not working, I'm getting 0 out of 10, my first question is always going to be, let me see your test code. Okay, let me see the main program that you wrote that calls your function 5 or 6 or 10 or 20 times with different test cases. And let me see which test cases you've run this on. Because the goal is to get some practice in testing your functions. Because outside of this class, you don't have an assess function, right? You're trying to write something that's never been written before. There's no assess genie that you can submit it to see if it's right. You got to figure out how to do that yourself. Okay, so there's some CSE 215, some inductive reasoning, and so on in there. But it's also about writing test cases. So what's a good test case? Well, it's something that stresses the edge cases. It's something that the best test case is the one that reveals that there's a bug in your code. But that's not a very useful definition. But how would you test something like this get first function? Certainly you want to construct a linked list in your array that's empty and pass that and make sure the error flag gets set and it returns a 0. And then you want to make a linked list that has a data value and make sure it returns that and error is 0. That's the bare minimum. But you can go pretty far beyond that. So what if you have the sentinel pointing to the very last element in your array, and that's where your first data node is stored? That could be an edge case. Because maybe you have something in your code which says if my index is bigger than or equal to 99, then report an error, right? And it should be if it's bigger than or equal to 100. So it's a separate problem figuring out what's a good set of test cases, right? But you want as many test cases as you can, and I'm very much in favor of swapping test cases with your friends. Okay, now you don't want to compare the code for get first, but if you're writing code to test your get first function, and you've got a program that calls that, right, you're all writing the same get first function, it's got the same prototype, the same expected behavior, feel free to go to a friend and say, hey, how did you test your function? Right? I'll give you my test code if you give me your test code, and test your function with somebody else's code. Because that's what's happening when you finally submit it for assessing, is you're testing it against my test code. Right? So as many test cases as you can think of, other people can think of, and the more you do this, the more you'll start to get better at coming up with test cases. Right? So let's look at some test cases. So here's my get first function, which almost works, but it has a glitch in it. But let's look at how I can drive this. So stdio node.h, we already did that. There's my main program. Here's my struct node array of 100 struct nodes. D, that's the name of my linked list in my main program. So I'm declaring that here. I don't declare that inside my function. Right? My function gets a pointer to a struct node, that's an array. Right? But if I declare this inside my function, I'm defining my own linked list. It's got nothing to do with what's being passed in. Okay, so my goal here, I want to make a little list containing 4 nodes, 10, 20, 35, and 50. And so I start off by setting up the sentinel. And I store the sentinel, well, so here's what my linked list is going to look like. Fuzzy again. So my sentinel is going to point to my first node, which has a 10. That's going to point to our second node, which has a 20. That's going to point to the third node, which has a 35. And that's going to point to the last node, which has a 50. So we're going to have pointer, 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 and a my_null. And we're calling this D. Now I could just store my first node in index 1, my second node in index 2, my third node in index 3. I wouldn't do that for test cases. It's too easy to get the code wrong but still get the right result. For example, you might say, oh, the first data node, I'll just return ll bracket 1.data. And if I stored my first node in d bracket 1, hey, my code looks like it works. How come assess didn't give me 10 out of 10, right? So scramble it up, make yourself a messy list. So I just did this at random while I was eating breakfast this morning. Arbitrary location. So Sentinel, I'm still storing a 42. It's valid, but it's pointing to index 7. So 7 is where I'm storing my first node. So at location 7, you can see I have 3 statements. Set the data equal to 10, set the next equal to 5, and set valid equal to 1. Which means index 5 is where my second node is, which should have a 20 in it. So my next set of 3 statements, d bracket 5.data equals 20, dot next equals 6, and valid equals 1. That tells me my third node is stored at index 6, and my next set of statements, sorry, that should have been a 2. So d bracket 5 dot next equals 2. And my next set of statements sets up the fields for d bracket 2, sets the data to 35, sets the next to 6, and valid to 1, which means the next set of entries is going to be at location 6, data is going to be 50, next is going to be my null, which is -1, and valid is still 1. So that set of statements initializes my D array to look like this. And I haven't filled in any of these other indices, or any of the ones between 8 and 99. But by filling these in, I've stored a list that looks exactly like this. Right? Doesn't matter what's in these entries. We know we started index 0 as a sentinel. The next node is down here at 7, that's a 10. The next node is at 5, that's a 20. The next node is at 2, that's a 35. The next node is at 6, that's a 50. The next node doesn't exist, that's the end of the list. 10, 20, 35, 50. All right, now I want to call my getFirst function and see if it's doing the right thing. Well, before I do that, I set this integer error variable to 99. Why do I do that? Because 0 is a pretty common default value. Depending on what kind of system you're running on, uninitialized variables could be set to 0. Lots of things will set things to 0. Not too many things will set things to 99. So if I call my function and I come back and my error is still 99, I know that I didn't change the value of that variable inside my function. Probably. But if I start off with error equals 0, I call getFirst, I come back, I check error, it's equal to 0, and that's what I wanted it to be, I'm going to think, hey, my function worked great, set error to 0. But how do I know that it actually did anything? It might have simply not changed the value of error. So I'm giving it a bogus value before I call my function, so that I'm putting the burden on the function to actually set that to 0 or 1 or whatever it's supposed to be set to. All right, then I'm going to call getFirst. I'm passing it my array D, which is my linked list. I'm passing it the address of error, and I'm storing the return value and result, and I'll print out result equals error equals, and that'll tell me if my function's doing the right thing. So my first node is a 10, so it should come back with error equals 0 and result equals 10, if it's working correctly. Did I compile? I don't know. I'll just say make, and then I'll run my main. And it comes back, result is 10, but error is 99. So I know something's wrong. I'm not actually changing the value of ERR for some reason. Well, let's try something else. Let's just go ahead and make an empty list. So yeah, I'm setting D0 next to 7, but I'm also going to go, and after that I'm going to set D0 to my null. I'm doing that so I don't have to delete that line, because I want to go back to it eventually. So by also doing this d bracket 0, dot next equals my null, I'm making an empty list. And so now it should return a 0 with error equal to 1. So let's test that. Hey, that looks like it works. So I'm doing something right in my code with the error variable. But when it's not an empty list, it's not clearing it to a 0 for some reason. Well, let's GDB it. Is this hard to read? How's that? Don't fall asleep. Better? All right, GDB, what's the first command that we execute? Start. That gets things rolling. There's a temporary breakpoint at the beginning of main. It's giving me extra information like argc is 1, means I had no command line arguments, that's fine. So I can say list and I can look at my code. And here's the code we're about to execute. So let's start executing this code. Now before we do anything, I can look at the current value of my array D. I can just say print or PD. And it's filled with all kinds of crazy numbers. Big numbers, negative numbers, all kinds of stuff. It's uninitialized. Saying struct node D bracket 100 says set aside space for 100 struct nodes and have D point to the first element, but it doesn't give a value to any of those elements. Okay, so we have gibberish loaded in there. That's okay. Let's start executing. So I'm going to say next, and I'm going to execute D0 data equals 42, D0 valid equals 1, D0 next equals 7. Now if I print D, you can see that this first set of values has my first node in it. Data equals 42, next equals 7, valid equals 1. We've created a sentinel node. And we've told it that the next node is going to be at location 7. But we haven't set up what's stored there yet. So let's do a few more next. So it's about to do D bracket 7 dot data equals 10. And here's the next, and here's the valid. And if we print D now, we can look at entry 0, 1, 2, 3, 4, 5, 6, 7. And there's our first data node. And we can do this more easily. If we just say PD bracket 0, it'll show us the fields of that struct node. Data is 42, next is 7, valid is 1. If we say print D7, it shows us data is 10, next is 5, valid is 1. So we can keep executing our initialization code. And now it should have initialized the entire linked list for us. So we can print D, and we could actually stare at this, maybe with a highlighter, and work through the linked list and draw this picture of 4 nodes, 10, 20, 35, 50, into the list. Or we can go through and just say print D0. That's the sentinel. The next node is index 7, so we can look at that node, D bracket 7. That tells us the next node is index 5, so we can print D5. The next node is index 2. The next node is index 6. And that's the end of the list. So there's the 5 entries in the array that correspond to the sentinel node and our 4 data nodes in order. Okay, starting with the sentinel and going to what it points to and what that points to and so on. Very, very easy at this point to see if something went wrong. If we see a crazy number in here, a negative 15 gazillion or something like that, we know something's wrong with the way our list is stored in our array. And we would go back to where that got its value from, and we would look at the code around there. Okay, no problem here because we just initialized with a bunch of assignment statements. Now we're about to set error equal to 99. So before we do this, error has some negative value. If I go ahead and execute that statement, error is equal to 99. Now we're about to call our getFirst function. This is where the action is going to happen. If I say next, it's going to execute everything inside getFirst before it comes back to me. And I'm not going to get to watch what happens inside that function. So if I want to step into this function, I have to say step instead of next. Okay, next is a step over, step is a step into. So here I'm going to say step, and now I'm starting to execute my getFirst function. And getFirst was called with two arguments, LL and error. If I print error, it's some big, long, awful number, right? It actually showed me already what error was. But remember, error is a pointer to an integer. So I can say, show me what error points to, and it's a 99. Now, LL is an array. If I print LL bracket 0, it looks exactly like D bracket 0. The reason is because LL bracket 0 is looking at the exact same location in memory where D bracket 0 is. Okay, it is D. LL and D are the exact same array. It's not a copy. They're both looking at the exact same location in memory, which means LL bracket 5 dot valid is exactly the same location in memory as D bracket 5 dot valid. Okay, which means that if we change LL bracket 0 dot data, it will change D bracket 0 dot data in my main. Okay, this is why we can pass arrays in C. So LL should look exactly like D. And the first thing it's going to do is check to see if the list is empty. If LL bracket 0 dot next equals my null. So it's doing this statement right here. And we just looked at LL bracket 0. We could see next is equal to 7, which is not my null. I don't know if it'll let us actually look at my null. I don't think it will, right? Because it's a pound define. It's not actually a variable in memory. So we have to know that my null is -1. But this if statement should fail, so it should not execute what's inside this if statement. So if I say next, it skips all the way down to line 13. Right, that's good. So line 7 was the if statement. If that's null, then it'll do the error and return 0 and so on. And it didn't do that. Instead, it came down to line 13. So it's about to say index equals LL bracket 0 dot next. Right, before that happens, we can look at the value of index. It's a weird number. It's to the 15th minus 1. So I can execute that instruction, and now look at index, and index is 7. Is that the value we wanted? Yes. Because when we made our picture of the linked list, we stored that first node at index 7. And so it's going to return LL bracket index dot data, and we can check the value of that, and it's a 10. And if that wasn't the value we wanted, we'd be looking right about where the error is at this point. Now we haven't changed error yet. We change error in this next statement right here. So we go ahead and we execute the next statement. And we're sitting here at line 16. This is the end of the function. And if we look at the value of error, it's still 99. It didn't execute this star error equals 0. Why not? Because we returned right before it. We said return, and then we said set the error to 0. Well, once you return, that next instruction never gets executed. So I put my two statements in the wrong order, that's all. So we can next one more time, and it'll come back in here into the print function, and here we can print ERR and see it's still 99. If I want to execute this print statement, I would say next. If you say step, it starts trying to debug printf, and that's a nightmare. But if I say next, it'll go ahead and execute that print, and then we're at the end of my program, and we say next once more. But we already figured out what the problem was, right? So we'll quit out of here, and we'll just swap the order of these two statements. We'll say make, we'll say my main, and now it works great. Result is 10, error is 0. So that's the kind of thing that you'll be doing a lot of with these programs and with GDB. And for PA1, you probably want to start by writing some initialization code to create a linked list, whatever you want the linked list to be. Okay, this one was kind of handy because it's got a set of nodes, and they're not stored sequentially. And now if you're trying to print your linked list, and it's blowing up, or it's in an infinite loop, or it's printing random stuff or something like that, right? Run through the debugger. Put a breakpoint at the beginning of the print routine. First thing you do, make sure the linked list array is what you expected. So print the values of the sentinel, print the node that that points to, and so on. If that's working fine, start stepping through your print code. And there should be something that says, you know, current equals sentinel, or ll bracket 0 dot next, and that should point to a node that has a 10, and then it should do something like print ll bracket current dot data, right, and that should print out the value 10. And if it's not happening, right, there's somewhere where you're telling the code to do something different from what you thought you were telling it. And that's the whole point of debugging, is to figure out where that disconnect is. So this is playing computer for you, right? Instead of working on a sheet of paper and writing down the values of variables and hoping that you're faithfully recording what each instruction is going to do, you have a computer right here. And you have GDB that lets you look inside it and see exactly what's happening. So each time that you say step or next, it's executing one more instruction, it's making some changes, doing some tests, whatever. You can compare what it's done to what you thought it was going to do. And there will be a disconnect somewhere if your program is not doing what you want. It's just a question of getting to that point, figuring out right here is where I thought it would do X, but instead it did Y, and then figuring out how to get it to do X. And you fix that one bug, you recompile, you rerun. If it's still not working, you go back in the debugger and you repeat. This is why it's nice to work with modular code, right? Because if you've got your main program and you've already debugged that and that's working, and now you write your search routine and it's not working correctly, you know it's somewhere inside this section of code from the beginning of search to the end of search, right? If you've got 15 routines in there, you don't know where to start. All right, does that make some sense? Cool. All right, so let me show you what PA1 should look like. Not the source code, though. So I'm running my main program and it's just giving me a prompt. You can put in a hello message or something like that if you want. But it's waiting for a prompt, and if I hit anything it doesn't recognize, it'll give me a brief synopsis of how to use this. So I can say I number, I can say P, I can say S number, I can say D number, I can say X. All right, so if I say P, there's nothing in the list, so it shouldn't show me anything. If it shows you one data value, which is your sentinel, you've got a problem. You're not ignoring the sentinel. Okay, so let's insert some numbers. Let's insert a 10, and let's see what our list looks like. Hey, it's got a 10. Not a big surprise. Let's insert a 20. See what our list looks like. It's a 10 followed by a 20. Are we actually inserting in sorted order? Because 20 is bigger than 10. Maybe it's just putting them in the order that I tried putting them into the list in. So let's insert a 15 and see if it gets sandwiched in between. Yes, it does. So that's good. What if I insert something that's already in there? That's an error. What if I try to insert the first node or the last node and it's already in there? That should give me an error. Those are edge cases, right? When you're inserting something, you may not check that last node. If that last node is 20 and you try to insert a 20, maybe your code doesn't look far enough and it'll go ahead and insert the 20 again. So these are good edge cases to check. I should be able to insert negative numbers, because those are valid integers. I should be able to insert a 0. I should be able to insert magic flags and not trip it up. All right, my search command should tell me if something's not found or is found. I should be able to search for the last thing. I should be able to search for the first thing. Deleting, I should be able to delete something from the middle, so I deleted the 10. And if I search for the 10, it shouldn't find it. And if I try to insert the 10 again, it should insert it successfully. And if I try to insert another 10, it should tell me it's already in there. So what did we just do? We deleted an element, we made sure it was gone, we searched for it and made sure it didn't find it. We tried reinserting it, that worked. We tried inserting it a second time, that didn't work. Similarly, I can delete the 10 and see that it's gone. If I try to delete it again, it should tell me it's not found. This will pick up all kinds of problems with the valid flag. It's tempting to write your code for search to just go through your array, check all the data fields, and see if you find your number. Don't do that. Okay? You got to start with Sentinel, see what node that points to, see what node that points to, and so on. And if you're just going through your array and you're just looking for this entry in the array somewhere, right, this will trip it up because I'll delete the 10, but it will still be found in there. Make sure you can delete the last entry. Make sure you can delete the first entry. Make sure you can delete everything except one node. Make sure you can delete the last node. All edge cases, right? And these are the kinds of things that I'll do when I test your program, okay? I don't have an exact test script written out, but these kinds of things. Have an empty list and try to delete. Have an empty list and try to search. And with the Sentinel node in place, most of these edge cases aren't actually edge cases in your code. But when you write code that doesn't have a Sentinel, right, all of these need special code to handle them. And if that code's not just right, these things will often give seg faults. What else is there we can do? That's probably about it. Insert, delete, print. That's pretty much it. Oh, try random stuff, right? Try those kinds of things. So those are some things to experiment with. But the basic behavior is just build a linked list. I'm probably not going to test trying to insert 100 things to blow it up because I didn't specify what to do in the assignment for that. And I don't have the patience to type in 100 insert commands. So, and in PA2 we won't run out of memory usually. So, but yeah, that's pretty much it for test cases. So that's the behavior of the program. Make sense? All right. Let me give you a preview of PA2. So you've got until Friday for PA1, Friday morning at 8 for PA1. But if you want to work on PA2 over the weekend, right, we don't meet again as a regular class session until Monday. So usually that last Wednesday, while you're still working on assignment N, I'll go over, or at least introduce assignment N+1, so that you've at least seen it and you can ask initial questions. N+1, it's an induction thing. There is no PA infinity though. So. Yeah, exactly.
I don't want him to prove that.
Does that mean there's out of programming assignments?
It could be.
We'll be in this class forever.
Yeah. Well, not necessarily. If you can do the first one in an hour, and the second one in a half hour, and the third in a quarter hour, then you can be done in 2 hours.
Prepare ahead of time.
Yeah. All right, so PA2. This reads very, very much like PA1. Okay, it's the same document with a few changes to it. Your linked list is constructed from struct nodes, but your struct node has 3 fields, but the third field is different. The first field is the data. Sorry, it's got 2 fields. The first field is the data. The second field is a pointer to a struct node. So we're not going to store these nodes in an array. They're just going to be floating around in memory. We're going to have the data, that's an integer, and then we're going to have the address in memory where the next node resides. And if we know where that address is, we can go to that address and find that node, find its data value, and then its next field is going to tell us where in memory the next node resides. So this is a genuine linked list. Okay, 2 fields, data and next. We don't need a valid field anymore, because anytime we have a node, it's going to be valid. If we're not using a node anymore, we're just going to get rid of it. We're not going to see it again, so we don't need a valid field. And in this case, when we're at the end of a list, this next is going to be set equal to null, N-U-L-L uppercase. That's a built-in symbol in stdio.h. So you can actually set a pointer equal to N-U-L-L, and it does the right thing. It actually sets it to 0. But we don't want to set it to 0. We want to set it to null. All right, so in your main program, you define a list like this: struct node star list, or LL, or whatever you decide to call it. So it looks like an array, okay, but in this case it's not really an array, it's just a pointer to a struct node. But in some sense, so was the LL we defined in PA1. All right, and then you're going to implement a set of functions which will look very familiar. One of these functions changes its prototype. That's the init function. So init takes no arguments, and it returns a pointer to a struct node. Okay, PA1, our init, took the linked list array, and I don't think it returned anything useful. Okay, init is different here. It takes no arguments, but it returns a pointer to a struct node. And at that struct node, you'll find the sentinel, pointing to nothing. So this initializes your linked list. So it returns a pointer to an empty list, which has a sentinel node pointing to null. All right, add is exactly the same, print is the same, delete is the same, search is the same. They each take a pointer to a struct node, and they take a number argument if you're doing something with a number, or print just takes a struct node pointer. Same prototype. So each node is a pair of entries, a data field and a next field, or null. To add a number to the list, create a new node, search the list for the proper place to insert the new node, adjust the previous thing's next field to point to the new node, and the new node points to the old next node. It's exactly the same. Okay, I just took the PA1 and edited it a little bit. So this all looks the same as it did before. Your main program looks exactly the same. Okay, the same interface, the same set of commands, the same expected behaviors. So no change to your main program other than having to define your original list as just a struct node star instead of a struct node bracket 100. And all the rest of this is exactly the same too. So behavior-wise, there's really no difference between PA2 and PA1. But what's going on under the hood is going to be very different. So let's look at some pictures. I'm fuzzy again, aren't I? Oh yeah. I need one of those test patterns from the 60s TVs. Yeah, yeah. Yeah, they have them in Fallout.
Yeah.
So let's suppose this is called LL. So this is a struct node star. And let's remember what a struct node looks like. It's got an integer data, but then it has a struct node star. Bless you. Called next. So here's the way to think of, one way to think about this in terms of what's going on in the computer's memory. LL is the address of a struct node. Okay, this is what we think of as a sentinel. So if I say, what is LL pointing to? It should be pointing to a data field in a struct node, followed by a struct node pointer, which we call next. So this might be our bogus value 42, and this might be some weird number, 7FF36. One of those weird numbers you get when you play in GDB. At location 7FF36 in memory, we should find another struct node. The first 4 bytes of that location contain the integer data value, which is say 10, and the next 8 bytes, if it's an 8-bit or 64-bit machine, might have some other hex address, right? 7FF44, and somewhere at location 0x7FF44, we're going to find another struct node. And that's got a 20, and maybe this has a 0x6066010. And at location 0x66010, maybe we find a 30, and then the Unix symbol null, which is a 0. So it'll be all zeros. And these are generally not going to be successive locations in memory. Just like in our array, they weren't necessarily successive. They could have been scrambled all around. Well, now they don't even need to be close to each other, right? So this might be stored at this location. It points to a node stored down here. That points to a node over here. That points to a node in some totally different section of memory. And that's the end of the list. But it's the same linked list. Sentinel 10, 20, 30, end of list. So our challenges are going to be wrapping our heads around mostly this, having a pointer to a struct node as part of a struct node. But if we don't think too deeply about it, it's really not that mysterious, right? It's a book where each page has a page number associated with it, and written on each page is some piece of information and the page number where you can find the next piece of information.
So choose your own adventure.
Yeah, that's really all that's happening here, right? And it's very much the same thing we were doing with the array, except that we weren't storing actual addresses in memory, we were storing locations in the array. And here we're actually storing a 64-bit or a 48-bit address that refers to some location in memory, right? But other than that slight difference in how you look at it, it's exactly the same as PA1. So for the most part, your code's not going to change except in a few spots. For example, and we'll do this more carefully next week, but for example, we had been saying, let's say we want to delete a node. And let's say this was previous and this was next. And we want to delete this node. So we've moved through the list and we've decided this is the node we want to delete, the node where next is and previous is the previous node. So in PA1 we're saying entry previous dot next should be equal to whatever the next node is actually pointing to. So it changes this field here to point over to this node. Okay, that's what we're doing in PA1. In PA2, we're not going to use the data, but I'll put it here anyway. In PA2, what would this look like? Well, previous and next are going to be addresses in memory. They're going to be pointers to struct node. So we're going to have struct node, previous, and next. and we've somehow marched through so that previous is pointing to this node and next is pointing to this node. Well, the next field of previous is going to be the thing pointed to by previous dot next. And that's going to be set equal to the thing pointed to by next, the next field. So star previous says the thing that is pointed to by previous. So star previous is actually this node. So star previous dot next is actually this node dot next. That's this field right here. And we're setting that equal to star next dot next. That's this field. So we're copying this value into here. It's exactly what we did up here with our code from PA1, but we're doing it with a slightly different syntax. Now, we're going to do this a lot. We're going to say, take the thing that this points to and give me a field from it. And in some cases, this thing itself is going to be a pointer to a structure. And we may want to say something like, take the thing that that points to and give me a field. And that may also be a pointer to a structure. We may want to say, take the thing that that points to. And we risk ending up with this weird notation. Right? And it gets really annoying really quickly. So we don't want to do that. So there's a different way to write this. And you've probably seen this before. It's this. And this means this thing in red. But it's a whole lot nicer to work with. So you can read this as, take the thing pointed to by previous and give me the next field, or the data field, or whatever field you're interested in. Okay, so it does two things. It dereferences the pointer, right, finds the thing it points to, and then it gives me a field. So a more general interpretation is something like pointer arrow field means star pointer dot field. They're exactly the same. And you can use this instead of this, but don't. Well, use this while you're trying to figure out what's going on. But pretty quickly you want to switch over to using this. And the reason is, if this whole thing, if field B of the thing pointed to by A is itself a pointer to a structure, and we want to access the C field of that, we can just write it like that. If we use the star notation, we have to say thing pointed to by A dot B, thing pointed to by that dot C. And this just kind of screams out, take the thing A points to, pick the B piece, take the thing that points to. Take the C piece. This will leave your head spinning. Okay, so we stick to this. And try to avoid that. So we'll definitely look at some examples of this, and we'll do some test code, and you'll have lots of ODPs next week, letting you get some practice with this kind of notation. But that's where we're heading with these pointers in PA2. So the other thing that changes with PA2 is memory management. So if we want to create a new node, we had a get node function that returned an index that was free in the array. We don't have an array anymore, so how do we get space for a new node? We're going to use Malloc. So Malloc is a built-in routine. You have to include standard lib. And then you can call Malloc and you can pass it an integer. And it will find that many bytes in memory somewhere, a contiguous block of that many bytes, and it will return the address of the beginning of that block. So if I have struct node LL, this is in my main program now. LL is a pointer to a struct node, but it doesn't actually refer to any particular location. If I wanted to initialize it in my main, I don't. I want to call the init function. But if I wanted to initialize it in main, I could do something like this. And I have to tell it how many bytes I need, maybe 32 bytes. And Malloc will find 32 bytes in memory, take the address where that block begins, return that as its value. LL will now refer to that block of memory. So now if I say LL arrow data, it'll refer to the data section of that block. And LL arrow next would refer to the next point, which is another struct node star. Does that make sense so far? So what about this 32? How do we know we need 32 bytes? We don't. Okay, you can go through, and if you know the architecture that you're running on, it's a 64-bit machine, so my addresses are 8 bytes, and my integers are 4 bytes. I need 12 bytes. So I could pop a 12 in there. Somebody runs this code in a few years, and they've got a 128-bit machine, and their memory addresses are 16 bytes, and you're only allocating 12 bytes, your code's going to break. Right? Somebody runs it on an Arduino, and they only need 2 bytes, and you're allocating 16 bytes or 12 bytes, you're wasting a lot of memory. So this is where size of comes into play. So size of takes a variable type and tells you how many bytes you need for it. And I'll say in general that's the only thing that you want to use size of for. How many bytes do I need for this type of variable? I want to store an integer in memory. How many bytes do I need? Size of parentheses int. I want to store a double. How many bytes do I need? Size of parentheses double. So in this case, instead of 32, I could say size of struct node. And the compiler will figure out how big a struct node needs to be, and it will basically replace that size of with that number. It's not a runtime call. Okay, it's basically a compile time thing. And I don't want the size of a struct node star, because that would tell me how many bytes do I need for the address of a struct node. That's not what I'm working with here, right? LL is a pointer to a struct node. That means the thing that LL is pointing to is a struct node. How many bytes do I need for that? The size of a struct node. Okay, the pointer is going to be relatively small, but if a struct node is 1,000,000 bytes, and this is a pointer to a struct node, I need to allocate 1,000,000 bytes and then have LL point to the beginning of that block of 1,000,000 bytes. So I want the size of the struct node itself, not the pointer. Yeah.
So do you put that size of struct node inside of Malloc?
Mm-hmm. So that would work. And you're probably going to have a statement very close to that inside your init routine. Because that's how you create a Sentinel node or any node. So your get node routine, sorry. All right, so the other difference between this and PA1 is that we don't have this, let me make sure what it was called, this get node routine that gave you an index in the linked list, right? Malloc is taking the place of get node. The flip side of that is release node. So you've created a struct node, and let's say it's equal to temp. So this is a struct node star. And let's say it's pointing to some node. And let's say we've deleted this node. So we took the node before and we changed its next field to point to the node after temp. And now temp is no longer a part of our linked list. If we start at the sentinel and we move through, it's going to get here, it's going to skip over temp. We're not going to see that in our list. But it's still sitting in memory. And if we let it sit in memory forever, eventually we might run out of memory. If we insert and delete a node a billion times, we're going to end up with a billion of these deleted nodes sitting around in memory. So we want to release this node back into the memory pool. That's what free does. So if you say free and you give it a variable whose value is some value that you got from Malloc, it will release that memory. It puts it back in the pool of available memory. And chances are next time we call Malloc, you'll get the same address back. But maybe not. So free will take the place of release node, and Malloc will take the place of get node. So you want to keep working on PA1. You want PA1 to be as solid as possible, right? And if PA1 is not completely done by Friday morning at 8, I suggest you keep working on it anyway. Even if you've turned it in and you're not going to try to, get more than 25 points off by turning it late, keep working on it through the weekend and get it as close to rock solid as you can. Because the better you understand PA1, the easier PA2 is going to be, right? Because it's really a few tweaks on the code, and it's things like changing this into this, or as we would write it now, previous arrow next equals next arrow next. Right, so this becomes this. I think that's all I've got to say for today. So Friday, 11 o'clock, right, section A is an open lab. So if you don't have a conflict and you want to come work on stuff, come then. I won't do any more ODPs this work. I'll probably post an ODP that will open Monday morning at 8. And we'll start hitting some ODPs next week, playing all the pointers and stuff. So we'll go over this on Monday, and we'll talk about PA1 also. And I've got office hours until 3 o'clock, so come by if you like.
Alright, I got this figured out. Question 7, the answer to question 7 and the answer to question 10 are wrong.
Alright, hold on one sec. Let me close out my recorder.